Section 32.2 Energy and Molecular Energetic Degrees of Freedom. Section 32.3 Heat Capacity. For monatomic gases such as helium and neon, the average energy is equal to 3/2 kBT plus the energy of the ground electronic state. Therefore, the molar internal energy is 3/2 RT plus the Avogadro constant times the energy of the ground electronic state. The molar isochoric heat capacity is the first derivative of the molar energy with respect to temperature, and it's 3/2 R. CPM is equal to CVM plus R, and that's 5/2 R, assuming the gas is an ideal gas. So if you look up the experimental value of the CPM of all monatomic noble gases, they are all 20.79 joule per Kelvin per mole. This is because this 20.79 is exactly 2.5 times R. For diatomic molecules in the gas phase, the average energy is 5/2 kBT plus half h nu plus this thermal correction to the vibration energy at a finite temperature, and then plus the ground electronic state energy. So over here, 5/2 kBT comes from the 3 translational modes and 2 rotational modes. This is the 0 point vibration energy. And again, this is the thermal correction of vibration energy at a finite temperature. And again, this is the energy of the electronic ground state. And if we multiply this by the Avogadro constant, we'll get the molar internal energy right here. This is the molar internal energy of the diatomic molecules. CVM, again, is the first derivative of the molar internal energy with respect to temperature when the volume is held constant. Therefore, if we take the first derivative of this term, the first term, it's 5/2 R. Over here, this does not depend on temperature. The ground electronic state energy does not depend on temperature. The third term over here, this does depend on temperature, but the dependence is very small, even at the room temperature. When the temperature is really high, indeed, this part will depend on temperature. I think this term is going to be approximately kBT when the temperature is really high. And kBT times N sub A, you get RT. So when temperature is really high, you need to include this term over here. And then CVM is going to be 7/2 R when the temperature is really high. Now the CPM is roughly CVM plus R, assuming ideal gas behavior. So the CPM of a diatomic molecule is roughly 3.5 R. So now let's look at the CPM of H2, O2, and N2. They are 28.84, 29.38, and 29.1 joule per Kelvin per mole. So if you look at these 3 numbers, they are very close to each other. This is not a coincidence. And if you divide these 3 numbers by 8.31446, you'll get 3.47, 3.53, 3.5. They are all very close to this 3.5 R. For linear polyatomic molecules in the gas phase, because it's a linear molecule, again, there are 3 translational modes and only 2 rotational modes. So this is the translational energy plus the rotational energy. Over here, because there are 3n-5 vibrational modes, so we need to sum up all those 3n-5 terms, one for each vibrational mode. And right here, this is the energy of the ground electronic state. So this number can be calculated using a computational chemistry software. And now if we multiply this by the Avogadro constant, we get the molar internal energy for linear polyatomic molecules. And then we get the CVM of this linear polyatomic molecules. It's roughly 5/2 R. CPM is roughly 7/2 R. However, when there are many vibrational modes with small wave numbers, or when the temperature is very high, this term will be significant. We'll have to take this term into account when the temperature is very high or when the vibrational wave number is very small. So if the temperature is very high, and then we have this KBT much greater than h nu, and then if we use Taylor expansion, the denominator becomes h nu over KBT. And then you have h nu divided by h nu over KBT, you get KBT. And KBT times this Avogadro constant, it's going to be RT. So when the temperature is very high enough that this KBT is much greater than h nu, and then we need to include 3n minus 5 this times this RT times RT. So this part is KBT, but KBT times the Avogadro constant is RT. So in that case, we'll have a much larger molar isochoric heat capacity. However, if we do not have many vibrational modes with a small wave number, and the temperature is low enough, so usually the room temperature is considered low enough for most vibrational modes. In that case, we can just safely make approximations and say CVM is roughly 5/2 R and CPM is roughly 7/2 R for linear polyatomic molecules. Now for nonlinear molecules in the gas phase, well, there are 3 translational modes, 3 rotational modes. Each mode contribute 1/2 KBT, and therefore you have 3/2 KBT for translational energy and 3/2 KBT for rotational energy. And over here we have 3n minus 6 vibrational modes. So this part is the 0-point vibration energy, or you can say this is the lowest possible vibrational energy. And over here, this is the thermal correction to the vibration energy. This part does depend on temperature, therefore this part may contribute to the heat capacity. Finally, you have this just the energy of the electronic ground state. Again, you compute this with a computational chemistry software. If we multiply this by the Avogadro constant, we get the molar internal energy. So it's 3RT plus the Avogadro constant times the average vibrational energy and plus this ground electronic state energy. And then by looking at this, we can easily evaluate CVM and CPM. CVM is roughly 3R, coming from here. CPM is CVM plus R. The result is 4R. CPM again is approximately 4R, assuming first ideal gas behavior, and second, the temperature is low enough that this h nu is much greater than KBT. When there are many vibrational modes with small wave numbers, or when the temperature is very high, this part does depend on temperature. This part is roughly KBT. So you are looking at 3n minus 6 times KBT. All right, and then multiplied by this Avogadro constant, the result is 3n minus 6 times RT. Therefore, the thermal correction to the vibration energy at a very high temperature is going to be 3n minus 6 times RT. So that's very significant. At the room temperature, this term still makes some contribution to the heat capacity. For example, the values of the CPM of ammonia and methane are 35.1 joule per Kelvin per mole and 35.7 joule per Kelvin per mole. And if we divide these two numbers by 8.3111446, so this is the numeric value of the gas constant. The result is 4.22 and 4.29. So both numbers are greater than 4. So the heat molar isobaric heat capacity of ammonia and methane are both greater than 4R. Not much greater, but about 5%, and this is 5% greater than 4R, and this is about 7% greater than 4R. Mostly it's because in ammonia and in methane, I think you have at least one vibrational mode that corresponds to the change of the dihedral angle. And usually that vibration mode has a very small wave number. And a small wave number means a greater contribution from this term. So that's why the CPM of ammonia and methane are greater than 4R.